Well, so today I want to describe irreducible representations. Irreducible representations of a symmetric group and their characters. So the results are due to Frobenius. Approach Frobenius. And a good exposition can be found in the book by MacDonald. Chapter 1 and section 7. I will try to present this approach in some more details. So what is the idea? Let's denote by this symbol the formal Z-linear combinations of irreducible representations. So I will not distinguish between representations and their equivalence classes. So there are finitely many. There are finite many irreducible representations of our group, and we also know what is their number. The number is equal to the number of conjugacy classes of our group. And so the number is equal to this quantity, the number of partitions of n, which is the same as the cardinality of a set of Young diagrams with n boxes. But we want to construct in a certain way the representations. So elements of this set are virtual representations, that is, linear combinations of true irreducible characters, but with integer coefficients which can be positive or negative. So one can say that.
Извините, а почему число классов сопряженности равно числу диаграмм, равно мощности диаграммы Юнга n?
Ну, у нас есть классы сопряженности. Классы сопряженности параметризуются разбиениями числа n. Это понятно? Это понятно?
Да.
Но у нас имеется взаимно однозначное соответствие между разбиениями числа n и диаграммами Юнга. Давайте я напомню, если у нас есть какое-то разбиение n1 плюс n2 плюс n3, то мы берем эти числа, упорядочиваем их по убыванию, возможно, не строгому, и рисуем диаграмму Юнга. В таком вот роде.
Да,
Скажем,
спасибо.
1, это 2, это... Вот. So we see that this This is a billion group by addition, which is isomorphic to, one can say, this lattice. Okay. Well, now we form the formal direct sum, which is by definition this abelian group. So we assume that this is simply this group. Okay? And we introduce the ring structure. We want make this sum of abelian group a ring. How to do this? We want to introduce a multiplication. We want find multiplication. Say this one. What is this multiplication? This is induction. Multiplication. This induction. That is, if you have two representations, E1 and E2, E1 is true representation, is a representation of this symmetric group, and pi 2 is representation of, sorry, it's okay. This group, we define this product. This is the induction to this group from this subgroup. And we take the exterior tensor product. Okay. So what we say, we have representation pi 1 G and pi 2 and G and H. G is permutation of SM. H is a permutation of the symmetric group, and we assume that we have a natural embedding. Natural embedding. And we define we have a pair. This is element of this group. And then we define it simply as this is an operator. Operator on the tensor product of the spaces. And then we take the induced representation. Okay? And all representations are regarded up to equivalence. Well, what next? We extend this definition to a map of this abelian group. By linearity. No? And the next observation, a simple observation, this multiplication is commutative. So we claim that the claim is that the induced representation is equivalent to a similar representation which is obtained by swapping this object. That is to this representation. So why? So this is an easy exercise. The reason is that the subgroups and so we just interchange or conjugate. That is, one can find an element, one can find element, the symmetric group, such that conjugation by this element transforms this representation to this representation because it transforms this subgroup to this subgroup. This is an easy exercise to see this. And from this claim, we see that our multiplication is commutative. The next claim is the multiplication is makes our associate. So we get an associative algebra. So this object is if what is this algebra? We want to understand its structure. So one can repeat all this in the language of characters. Because we know that representations are determined by their characters up, exactly that up, representations up to equivalence can be identified, can be determined uniquely by their characters. So let us denote in a little bit different ways. Some other notations say R, and the the linear combinations of irreducible characters. So again, this is an abelian group. Again, this is exactly, essentially this is the same. Again, this is isomorphic to this group. And we know that induction of representations corresponds to induction of characters. So we can define product. So we can see, maybe again set. This is the direct sum of these abelian groups. And this is in associative algebra. And this is a graded algebra under multiplication. Cross. In Russian one can say умножение кружочком. So if you have to, more generally, one can work with a tensor product. This abelian group tensored with the field of real numbers. So this is same as the direct sum. So this simply means that we take linear combinations of irreducible characters with coefficients in real numbers, not only integers. Is it clear? Or maybe some questions? Okay.
Извините, а вот под тензорным умножением, вот там целые числа мы рассматриваем, а можно вместо ZR поставить вот в такой записи?
Какой записи?
Ну вот вторая строчка снизу, справа формула, там есть тензорное умножение, под тензорным умножением там Z стоит. Можно вещественные числа поставить там?
Ну, нельзя поставить, потому что у нас изначально этот объект определен над целыми числами.
Спасибо.
Ну, это я написал формально, это в сущности речь очень простая. Это просто конечномерный вот этот объект, это конечномерное векторное пространство вот этой вот размерности, базис которого это неприводимый характер. Вот чего тут особенного. I defined previously the induction of central functions, and characters are central functions. So the multiplication here is just induction of central function. So if you have to, this is a central function on this group, in chi2 is a central function in this group. We take this central function of this subgroup which is subgroup of this symmetric group, and the product is according to the formula, to the general formula, is as follows. We take the sum over which means that we take some representative of these cosets, and we take this function, which is a function on this subgroup, okay? And then we extend it to the whole group by taking it, by setting it 0 outside this subgroup. So this is the notation to indicate that we extend this function initially defined on this subgroup to the whole group. And next, this is the definition, and we take sum over the representatives, Here G is an element of a bigger symmetrical. And again, from the fact that when we interchange these two subgroups, we obtained a conjugate subgroup, we see that this operation is commutative. So we see that is a commutative ring, commutative, say, algebra over this ring. Its tensor product, is commutative algebra over the real numbers. So we want to understand the structure of this algebra. So the final result, we will see that this algebra is naturally isomorphic to the algebra of symmetric functions. So this is the key result. Let me explain how one obtains this isomorphism. And using it, we can compute, in a certain sense, the irreducible characters. Just a moment. How to do this? Let me recall the definition. Rho is a partition of n. Rho is a partition n, which can be seen as a Young diagrams, but we prefer to write it in the multiplicative form. So on. And I recall the notation. The quantity 0 is defined as follows. This is the product numbers. What is the sense of this quantity? We know that if that to rho, there corresponds a conjugacy classes. Class C rho of a symmetry group. Yeah. And a simple exercise is as follows, that the number of elements in this conjugacy class is equal to n factorial divided by this quantity. This is because that this quantity is take some element, say assume G is in this conjugacy class arbitrary, and consider the centralizer of G, that is the set of permutations which commute with this G, and we have this equality. And from this one can conclude that we have this one. So this is the meaning of this quantity. What next? Let's define this symbol, a characteristic function, of a set 0. This is a central function because this is a conjugacy class. And the key formula is as follows. So assume that rho is a partition of some number m, and sigma is a partition of n, and let's take the product in our sense of these two central functions, which is the product defined through induction. I mean, the product is defined by this formula. Okay. So one gets some central function, and this characteristic function form a basis in the space of central functions by the very definition of because any central function is characterized by the fact that it is constant on conjugacy classes, and so we see that such functions form a basis. So we want to understand what happens after multiplication of two conjugacy classes in this sense. And the result is as follows. This is equal. Let me write, and then I will explain. Very simple formula. So what I need to explain, what is this meaning? But this is very simple. Assume that we have some partition. So rho is a partition. Let me write more correctly. So a partition is a decomposition of a number into a sum of positive integers. So we can write this is a collection of numbers, positive numbers, such that their sum is equal to n. Likewise, this is a collection of positive integers, and their sum is equal to n. Now we just take the disjoint union. Is this collection this is a partition, of m plus. So the point is that first we view this object as an unordered partition. So the order is not essential here. But just for convenience, we can reorder these numbers in a weakly decreasing order. So we can assume that usually. But if you take the disjoint union of this number, we can reorder them in weakly decreasing order. We get another partition or another Young diagram. Is it clear or not? Okay. So, for instance, if you have something like rho is, say, sigma is this union is 7, 3, 2, 1. Okay. So let's prove this formula. Proof. So let's introduce the notation. Given a central function, given a central function phi, set modulus of phi is the sum of its values. In our situation, all these values are non-negative, so one can say this is the total mass phi. But in principle, it can take no negative values. So this is a formal definition. Okay. So what is the proof? The proof from the very definition, from the formula, for this multiplication. Let me recall this formula. This one. We apply this formula in the case that chi1 is this and chi2 is this. And we see immediately from this definition, just look this picture and this, we see immediately that one get a central function as the result of multiplication. The result should be proportional to simply to this one. So what we have is equal to some constant. So our task is just to understand what is this constant. But the next observation from the multiplication one sees that in general this mass, the sense that I defined it, is equal to the mass of one function times the mass of the second function and times this quantity. Sorry, this one. This is because this quantity is equal to the cardinality this. This just corresponds to summation of the representatives of these cosets. And now we see that this quantity is nothing but the cardinality. This is this one, and this is equal to this equal to and combining these expressions, okay, one sees that the constant should be equal to this one. Okay. So this is the end of the proof. Some questions maybe? Well, now we defined definition of definition of characteristic map. from this to the algebra of symmetric functions. The definition is as follows. This map is defined by this symbol. We defined it as follows. Maybe it's better to we defined it as follows. We said we assign this characteristic function times this constant. We assign to it the symmetric function P. This is the definition. Okay. So this is an additive map. This is an additive map because these functions say, so this is the map. This is a linear isomorphism R because the functions form a basis, and the corresponding symmetric functions E O form basis of the nth homogeneous component of the algebra of symmetric functions, also over R. So we just assign to one basis, this basis, to this basis. So this is a linear and graded isomorphism. The next claim, the linear map, characteristic map is also isomorphism of rings. That is, it is consistent with multiplication. So what this means? This formula so this formula is equivalent to the following one. Multiplied by this is why I want to deal with these functions and not simply this. This normalization is convenient because the multiplication becomes especially simple if we multiply if we use this factor. So just look at this formula and compare it. So compare. We compare two formulas. One is another is this one. This is multiplication. In algebra. And this is multiplication in this algebra. Algebra of symmetric functions over real numbers. So we see that these formulas are the same. In both cases, multiplication just reduces to concatenation of partitions. So in both cases, multiplication looks as concatenation of partitions. And this holds by the very definition of the power sum symmetric functions. Is it clear or some questions? So please ask. No questions. Well, so we get the isomorphism. The isomorphism, right? It's an isomorphism. So we see that the algebra, we conclude the algebras seem isomorphic. What next? Next, we definition. The definition is as follows. Let denote a trivial one-dimensional characters of a symmetric group. So this is simply the constant function. So this is the constant function, constant one on the group. So we can apply to use the characteristic map. So apply to this, the map. What we get? We have this claim that the characteristic map is equal to the H function. How to prove this? How to prove this? And we see the proof. We see that this function, the constant equal to 1, is simply the sum of all characteristic functions of the conjugacy classes, just by the very definition. We can split our group into the disjoint union of conjugacy classes, and then we see that the constant 1 is equal to the sum of these functions. So we see that follows that the image of this function by the characteristic map is the sum of this object, but this is equal to the sum of this. This is equal to this, so we just get this sum. So the claim is now, so the claim now is that we have the following equality. The sum of these quantities is equal to this. And how to prove this? This is an exercise we can deduce. Let me omit the proof. This follows from the equality relating the generating functions. So the left, this means that we have equal to the exponent sum amazement. So we take that Hn is the coefficient of Tn in the right hand side. And using the very definition of the exponent, we get this formula. This leads to this formula. Okay. Well, the next claim is as follows. Is the characteristic map is isometry. Let me recall that we have inner product, scalar product, product in the algebra of symmetric functions. I defined it. And we have also the product on in the space of functions on the symmetric group. Space of functions inner product.
А как оно там определено?
Вот я сейчас говорю. Кто как определен.
Скалярное произведение в симметрических функциях.
Но я его определял. Давайте я напомню.
Нет, SN, вот для группы SN имеется. Вот я.
Да, вот я напоминаю. Definition is quantity. This one. Keep attention of this factor.
Спасибо.
So the claim is, so what we have. So this formula determines scalar product in, because it is contained in the space of functions in the set by the very definition. These are central functions, and in particular, we can apply this definition to scalar to central functions. Okay? And we assume that, so we assume that the decomposition is orthogonal. Meaning that the different components are pairwise orthogonal. And this corresponds to the fact that different homogeneous components in the algebra of symmetric functions are also orthogonal by the very definition. I recall that the scalar product in the algebra of symmetric functions, in this algebra, is determined by the fact that definition is the Schur functions are orthonormal. Okay. Now the claim is this one. Its map is isometry. It is an isomorphism of algebras, but it's also isometry of spaces, of linear spaces. How to prove this? But we just, our construction is related to power sum symmetric functions. It's not it's not directly related to Schur functions, but we need to know what happens for the scalar product of power sum symmetry function. But we know this. Why? We know, so the proof. We know, I proved this. We know that this scalar product is equal to this quantity, this same quantity. Okay? And we know that by the definition scalar product in the space of functions, we see that we take, so maybe it's better to write, suppose. Our some symmetric functions are orthogonal. Not orthonormal, but orthogonal. This is Kronecker delta. We know that I proved this correlation, okay? But on the other hand, we know, it's easy to see, that these functions are also pairwise orthogonal. This is easy to see. So we have also have Kronecker delta. And the factor is this one. And the factor is this one. Why? And this is because the orthogonality is obvious. So the question is only about the factor. This is what we see, that the scalar product for these functions with itself is equal to these factors, because it appears in the formula. This factor appears at the very beginning. And next we have summation of constants which are or equal to 1. So we get this. But what is this? And this is equal to this quantity. And after cancellation, we get this one. So we get this formula. Okay. But this formula is equivalent. This is equivalent to saying that you multiply then we get, what we get is this is 1, this is 2, and we also say, let me also write
А дельта-символ нужен в формуле 2?
Не нужен, да, я просто напишу еще раз дельта символ. Поскольку они ортогональны, то здесь надо поставить ро, сигма. Давайте лучше я это введу. Now we see that we prove just compare. And because we know that by the very definition, we see that the image of this function is the symmetry. So we see that the scalar product is exactly the same. The next step is I recall the Jacobi-Trudi formula. Trudi formula. It says us that sure symmetric functions is equal to the determinant of the H functions. Well, in this formula, one can assume, it's convenient to assume that so one can assume that how to see this better. Just a moment. Okay, so we can assume that I J range from 1 to K, where K is equal to the length. It's convenient. We can take any number which is greater or equal to the length, but just take this one. Okay. And from this, just take, so from this we deduce, from this, and this formula, we get what? Take the determinant. Let me write as follows. So what means this notation? We just take the determinant. Just take the determinant, but we just expand. Just expand. Okay. Just expand, and you get some alternating sum of products, but just regard products as with respect to this multiplication. So the left hand side, left hand side is equal to what? Just the sum of the permutations. How to write permutation, say tau. Even the sign of a permutation. Now we take times so this is an induced function. Okay? So each with these quantities is an induced function. And by the very definition, if some quantity is negative, then the whole product is said to be equal to 0, just as in the definition of this determinant, because we assume that these symbols are by definition equal to 0. And exactly according to this prescription, we understand this formula in the same way. And if all these quantities are positive, we just have a partition, of n, and this makes sense to this expression. So we get some central function of the group S of n, and we apply to it characteristic map. And because we proved that our map is a ring isomorphism, and because we know that these elements are mapped to corresponding complete homogeneous symmetric functions, we see from the Jacobi-Trudi formula that we have this. Okay, let me stop this moment. I will continue the next lecture. Just maybe it's time to stop, and if you have some questions,